Hello, good afternoon, or good morning, wherever you happen to be in North or South America today. My name is Jason Hodgert, and I'm going to be introducing the webinar that we're about to give today. I'm just going to give a couple of moments to get some of the other people to get into the room here. We have a pretty full house today, which is exciting. We're glad everybody was able to take time out of their day to listen to our presentation, and we hope you enjoy it. So today's presentation, the webinar today, is agricultural monitoring workflow using Geomatica and free Landsat-8 imagery. And what we're going to be showing you today in some software demonstrations is how you can use freely available Landsat-8 imagery to use that as an initial no-cost pass to monitor agricultural crop health. This is going to let you identify potential vegetation stress to commercial farmlands or any farmlands, any kind of vegetation you might be monitoring. And if indications of stress are identified using the Landsat-8 imagery, analysts can then collect higher resolution imagery such as rapid eye, which is what we're going to use further on in the demonstration, for a more detailed investigation into the agricultural fields. And this helps ensure that you're purchasing the data that you need. Using a low-cost solution or a no-cost solution like Landsat to identify larger areas that might need more attention is great as a first step so you can really pinpoint what you're going to what areas you need to focus on with your high-resolution imagery. So before we get completely started, I want to just sort of go over the housekeeping and the rules and the interface of the GoToWebinar system that we're using. All your lines are muted during the course of the presentation, so you can talk amongst yourselves and make noise and type away, and you won't be interrupting the presentation at all. During the course of the presentation, if you have any questions, there is a questions box on your panel, and feel free to enter your question at any time. You don't need to wait till the end. We will be having a dedicated question and answer session at the end, but if you ask your question when it pops into your head, one benefit is that you're not going to forget the question by the time we get to the end, and plus you can get it loaded up in the queue so we don't run out of time before we have an opportunity to answer your question. Lastly, if you're having trouble hearing the audio, you can probably read that slide but not quite understand what I'm saying. You can let us know by typing a question into that box or question into the box or raising your hand. So one of the things we like to do here when we do our webinars is poll the audience. We like to get to know a little bit about who's viewing our webinars, and this allows us to get a gauge on whether the information we're presenting in these webinars is useful, if we're targeting the right audience, and more importantly, it allows us to direct our efforts and our software development towards the customers that are interested in the solutions we're providing. So the first poll I have for you today, I'm going to have 3 quick polls throughout the presentation, is we'd like to know a little bit about yourself. If you could let us know a little bit about your background and your interest in this webinar, that would be great. We have a few options there. Perhaps you are a student and you're studying this topic at school. You could be some sort of an agronomist or a GIS specialist that's providing services to the farming industry. You could be a scientist that's researching remote sensing uses for agriculture. You could be with the local government and you're using remote sensing to do policy analyst. And or you could, obviously there's lots of other jobs other than what I've just listed. And if you do select the other, feel free to enter into the question box what area of work you're in, because it does help us target our webinars and target our work much better. Seems like most people have had a chance to answer the poll, so I'll shut that down and I'll just share some of the results. The majority of people here are scientists researching agriculture and remote sensing, which is great. This is definitely an audience that we are familiar with, and you are familiar with us as well, and a pretty even split amongst the rest of the choices there. On to our presenter. Today, presenting, we have Mr. Sean Malamed. He's an application specialist here at PCI Geomatics, and he's responsible for providing, among other things, pre-sales engineering and technical marketing support. Sean's been with us for a few years, and he's worked all over the company. He's worked in development and quality assurance, and really is a jack of all trades and knows our software products inside and out, as you are about to see during the demonstration. One more poll before I get out of your way and let Sean deliver the demonstration. And this is specifically about what kind of data sources are you using in your agricultural analysis. You could actually be sending people out into the field to collect field data and sampling the crops and the plants that way. Of course, aerial and satellite imagery that we use quite often in remote sensing. You could use a combination of both, or a completely other form of data collection as well. And in this poll, feel free to click all that apply. Excellent. Thank you again for taking part in the poll. Just to share the results, pretty even split across. Everybody's pretty much using a mixture of everything, but satellite imagery definitely has the lead with about 60%, at least answering at least once that satellite imagery is your primary data source for this kind of information, which is excellent, which leads us right into the presentation that Sean is about to deliver here. So I'm just going to hand it off to Sean right now, and he'll be able to continue from here. Go ahead, Sean.
Just take 2 seconds while I show my screen here. Okay, so as Jason already mentioned, we are going to be spending the next half an hour or so, 45 minutes, to basically discuss how Landsat, or freely available Landsat imagery, can be used in conjunction with other higher resolution commercial remote sensing data in order to perform various agriculture applications. So during this presentation, during our demonstration, the first thing we're going to discuss is just a little bit about the importance of the Landsat continuity mission. We're going to also just briefly show you the one different technique for acquiring the imagery for those of you who may not be familiar with Landsat data and how to obtain it. And then we're also going to show you just some other resources in which you can follow in terms of how to acquire and make use of the Landsat imagery. Afterwards, we're going to go into our first use case, which is what we're calling low-cost precision farming and cross-cueing of different sensors. Now, I just want to make sure that people are aware that when we say precision farming, we are working in the terms of a remote sensing concept and a satellite concept for that matter. So we're still working from about a 5-meter resolution. What we're trying to do is basically hone in on key areas in a larger commercial field in order to identify stressors and then what might be the actual cause of the stress in the field. And then after that, we're going to go into another very brief demonstration or use case of seasonal monitoring using Landsat-8 imagery only, and how it's a wonderful tool for quick seasonal monitoring, a very quick application along with Geomatica. So as mentioned, let's first take a look at the Landsat continuity mission. So the Landsat data continuity mission really had the objective of providing consistent and continuous coverage of the Earth's surface, and specifically freely available data, or data that's available to the public domain. This is one of the reasons why it's such a valuable resource and a valuable resource, and very important, especially in different applications such as agriculture and also mapping the surface changes on the Earth. Now, a quick little timeline over here. We can see that we have, since the Landsat 4 mission all the way up to our current Landsat 8 mission, we've basically been able to acquire the 30-meter thematic mapper bands, which include the visual near-infrared, middle infrared, and then the thermal infrared, which is actually at 120-meter resolution. So the Landsat 8, which was launched earlier this year, is now operational, and data can be obtained for the Landsat 8 mission already on the various different methods such as GLOVIS, or USGS's GLOVIS website. So what are some of the important values of Landsat data? Well, they have a few achievements. One is that they have continuously captured imagery for over 30 years. This is really the longest continuous record of Earth's surface as seen from space, and that's a direct quote from the NASA website. And that is a really impressive concept if you think about it, is that really if you want to map out the changes of the Earth through a long period of time and see how the different effects of land classification has changed throughout the years, well, Landsat is a wonderful data source for viewing these changes. It has continuous 30-meter resolution imagery for most areas on Earth since 1982, and this is true for the visible, near-infrared, and middle-infrared portion of the spectrum. And then it's also one of the very few commercial satellite sensors out there that provide a thermal imaging band, and it's at 120-meter resolution. So obviously some of the benefits is that it's freely available and it's also up-to-date imagery that you can obtain from the Landsat 7 and 8 sensors. Landsat 5 was recently decommissioned earlier this year. It also has huge archives of imagery dating back decades, which is another, as I said, is another great source for looking back to see how things have changed since the inception of the Landsat mission. Another really important aspect is that it has the same ground resolution and spectral filters from the Landsat 4 to the Landsat 8. The only difference is that the Landsat 8 has some new bands now. So this is really important as it's very easy to do direct comparisons. And they also provide geometrically accurate ortho images. And this is very important for applications outside of agriculture, or even including agriculture, just in general remote sensing applications, as this imagery can often be used as a reference source for orthorectifying other sensors, or imagery from other sensors. So PCI Geomatics has been around since Landsat has began their mission. And we really are one of the first commercial softwares to try to support the Landsat 8 sensor. We offer complete data and metadata support of the Landsat images, which allows us to take special advantage of the Landsat data and take advantage of some of our algorithms such as atmospheric correction for quick and easy setup of what's an otherwise relatively complicated operation to perform. So PCI Geomatica also supports a variety of different advanced algorithms that are specifically tuned for Landsat or include Landsat as one of the supported sensors. And this just gives you a very short list of some of the different algorithms and operations that are either tuned for Landsat specifically or support Landsat as well as other sensors. So a quick note about acquiring Landsat imagery. So I'm going to just very quickly show you the GLOVIS website, which is provided by the USGS. And it makes it very easy in order to find Landsat imagery and then download it. So the USGS has provided this website, glovis.usgs.gov, for those of you who are not familiar with it. And it allows you to search throughout the entire globe all the different data available in this repository. Now by default it's going to show the most recent up-to-date imagery, which you can see here is a Landsat 8 image. And if we're interested in this scene, we can zoom in to a closer resolution to get a better thumbnail or a better idea of what this image looks like. And then if we want to download it, we can simply click Add and then Send to Cart. And then of course we are required to log in, so you do need to sign up for this. But it's free to sign up, and it's a wonderful resource for obtaining imagery. And of course it also includes a variety of USGS other USGS data that's available, such as ASTER EO1, the Landsat archives, which include Landsat all the way back to Landsat 1, and of course the Landsat 8 images that are being acquired now, as well as a variety of other very important spaceborne imaging sensors. Another quick and wonderful resource, which I just want to show you, is if you go to the PCI Geomatics website and go to Resources, PCI TV, And you can go, for example, to our Tech TV section, and then we have a YouTube video that has been developed in order to show you the different methods for downloading Landsat-8 imagery and then making use of it. So there's more than one way, and Glovis is just one way that I actually prefer to use, but there's many different ways in which you can acquire Landsat-8 imagery, and this video goes through a variety of them. So it's a highly recommended video to watch if you're interested in acquiring Landsat-8 imagery and seeing how to make use of it. So that's really my sort of overview of the Landsat continuity mission and why it's important, and then how to obtain the data. So this leads me nicely into my first use case application, which is precision farming in the context of remote sensing or spaceborne remote sensing, and then specifically cross-queuing Landsat and rapid eye imagery in order to minimize our costs. So our objective in this analysis would be to lower costs and increase efficiencies for the management of agricultural fields, specifically larger agricultural fields. We're going to look for areas of low vegetation cover and signs of possible stress due to nitrogen deprivation. So for those of you who are not agronomists or not very familiar with the agricultural field, particularly students potentially, crops and the growth and yield of crops are highly dependent on nitrogen. So it's one of the more important aspects that can dictate how good of a yield and how healthy your crops might be. So it's a very important sign or indicator in order to identify whether or not corrective action needs to be taken on certain areas in a field. So by performing cross-queuing of two different sensors, we're really able to accomplish both of those objectives. So first, we can use the freely available Landsat data as an initial pass to just see whether or not we believe there might be a sign of a problem in one of our agricultural fields. So we're able to lower our costs by using Landsat data initially. And then we can purchase only the data that's necessary in order to perform our analysis on the fields that we identified as being potentially problematic. Now this is not just for satellite. For example, if you also have contracts with airborne companies where they fly airborne sensors, hyperspectral companies, you can also use this as a technique as well. So let's take a very quick look at the workflow that we're going to utilize in this demonstration. So as mentioned, our initial assessment will be using Landsat imagery. We're going to compute a very basic vegetation index. So I'll show you the two that I tend to use with Landsat imagery. And then we're going to highlight possible problems in our fields that we're responsible for. So in this scenario, we're going to be a company, an agronomist, for example, where we're actively monitoring a variety of different commercial agricultural fields. So we have different customers, and we want to highlight and identify which of our customers' fields might require additional analysis. So this then leads us on to the next step, which is doing the thorough assessment. So we're going to obtain the rapid eye imagery. We're first going to co-register the rapid eye imagery or orthorectify it using the Landsat as a reference. We're then going to perform atmospheric correction to convert the at-sensor radiance values to ground reflectance values so that when we compute our chlorophyll index, that it can be more reliable and more stable. Also, this index that we're going to be using does require that the measurements are in the reflectance domain, so it is a prerequisite to perform atmospheric correction. And then from there, we're also going to compute our leaf area index so we can do a cross-reference between the chlorophyll index and the amount of density in terms of the leaf coverage or the canopy cover. And then we're going to simply assess the results. And then, of course, we could make a report and then take corrective action if required. So step one, acquire our Landsat image and perform our index. So in this case, I've just provided two very common, well-known indices. The first one is the Soil Adjusted Vegetation Index, which is really an extension of probably the most popular vegetation index known as the Normalized Difference Vegetation Index. And all it does is it includes a special coefficient, L, for adjusting for soil, the influence of soil in the fields. Obviously at this resolution, 30-meter resolution that is, there's going to be a lot of spectral mixing that's happening. So by trying to reduce the influence of soil and only to obtain the vegetation components in a given pixel can be a useful method to help really assess our areas. And then this diagram provides a good example of what we're looking for. So we're actually going to zoom into a given crop that we're assigned to or contracted to assess and monitor, and we're going to apply an enhancement in the NDVI result, and we're going to look for specific patterns of where there might be a lower NDVI. So this is obviously not a guarantee that there's a problem here, but it's a sign that there might be a problem. Now, if it was just random noise or speckle, then likely it's just when we zoom in to apply our enhancement, it's likely just that there's very small variations and therefore not really worth looking into. So let's just take a look at this concept. So I've opened up Geomatica Focus, and I have here loaded our Landsat image. Now this is a Landsat-8 image because we're working with data that we have currently. But of course this concept works with more modern data. And I'm zooming in, and what I have outlined here in yellow are my different crops that I'm responsible for in terms of monitoring. So a variety of areas throughout this region. So I'm now going to zoom in, the first thing I would do is compute my vegetation index. So there's so many different vegetation indices out there, and whether you are interested in performing an NDVI or not, or SAVI, or even your own index that you might have developed for your own purposes, you can do this using our raster calculator. And it's a wonderful tool in terms of applying your own custom operations and calculations. So in this case, I just input the NDVI calculation, but of course you could create your own, such as the TDVI is another more popular, more complex vegetation index. So this is just one of the tools that can be used in order to calculate your own custom vegetation index. So with our NDVI calculated, we're basically going to zoom in. So I'm going to pull up my fields here, go to my attributes table, and let's take a look at the Jones's farm. Well, this is actually the one that we were looking at originally. So we can see in this outline here that there's a pattern based on this enhancement. That's a little bit concerning, so I might go and take a deeper look at this field. Now obviously it just might be that this area is really, really high NDVI, and then this is just not quite as high. That's a possibility, but it's just a potential area of concern, so it's worth further investigation. Now if we move over to the Smith's farm, we can see here there's another little area of concern as well. Remember, these are 30 meter by 30 meter pixels, so this is not really that small of an area. There's other areas here that show signs of potential stress or areas where it's more sparse, and perhaps we need to investigate as to why. Now I can go, of course, to other ones. We can see here that it's just a very low NDVI. So if I turn on my multispectral image, I can see that it's a fallow field. So this one obviously does not make sense to investigate. And I can continue on with this throughout a variety of my different contracts. I can see that this one's pretty consistent, so I'm quite happy with it. so don't necessarily need to go on. And I can continue on and on. So ultimately, I've then now moved on to the stage of identifying the problem areas. So if I look at my fields here, I basically categorize them as 3 different possible field types. Fallow, they pass, so I'm not very concerned about them, or a warning in red. So as we can see, there's a large geographic difference between these two. So what I'm going to do at this point is I'm going to load our rapid eye image that we obtained. So this means that because these areas are outside of our current image, I was able to purchase the amount of data that I needed to perform my analysis. Because I don't need to perform analysis on these fields, I don't need data for this area. So I can help to keep my costs down. Okay, so moving on. So why rapid eye? Why are we using rapid eye as our sensor for performing the higher resolution, more detailed analysis? Well, there's a few very important reasons as to why. One is that it's one of the only few commercial satellite sensors with the red edge band. The red edge band is known to be sensitive to chlorophyll, which is a strong indicator of nitrogen levels. There's a lot of studies going on to show the correlation or the relationship between chlorophyll and nitrogen. Now, we can take advantage of the red edge vegetation indices by using the rapid eye data, which rapid eye, as mentioned, is really only one of, I think, 2 sensors that I'm aware of, commercial sensors that have the red edge band. Now, some of these indices we're going to use are more developed towards hyperspectral, so more narrow bands, but they've been successfully applied and tested in certain scenarios with a more broadband sensor such as rapid eye. Another important note is that it's affordable. Rapid eye provides very large footprints, and they provide a variety of different footprint sizes, so you can really customize the data that you need. So obviously this usually corresponds to less data is required to purchase. Higher resolution. It's suitable for precision farming analysis on larger agricultural fields, and once again when I say precision, I mean in the context of remote sensing or spaceborne remote sensing. So it's resampled to 5-meter resolution. And then it also has a very high repeat time. So whenever we have our Landsat image, it's likely very possible that we can get a rapid eye image collected on the exact same date, which is also a very nice concept. And that is the case in our example here. So as you can see, the first most important, or not most important, but a very important component is to orthorectify our image. So orthorectification using Geomatica is very valuable because it, one, is often less expensive than purchasing ortho images from the vendor. It's very easy to do with our automatic GCP collection techniques. And then we already have our Landsat image, which we're using as a reference. And by orthorectifying it ourselves, we're ensuring a co-registration with our Landsat image. If you get it provided by the vendor, there's no guarantee it's going to line up with your Landsat image. And then the next one is doing the atmospheric correction. So this is required to remove noise in the signal due to atmospheric effects. So scatterers, absorbers, attenuation of the spectral bands. So a lot of this information, as the information received at the sensor, is what's called at-sensor radiance. And these are often scaled as are provided to us in a 16-bit or 8-bit channel. And therefore, the actual measurements themselves have very little meaning. And even if we were to convert them to just radiance, like unscaled radiance values, there's so much atmospheric effects that we really don't know what we're looking at. So what we have here in this example is that this is a vegetated field for the rapid eye data before calibration or before atmospheric correction, and you can see that we have a much larger measurement in the blue band than what should be. And this is very much a result of the fact that blue is a very predominant scatterer. And then ground reflectance, so once we performed our atmospheric correction, we can see we get a much more stronger correspondent, or a much more, I guess, curve that is much more common to what you would expect with agricultural fields or a vegetation field. And this is also an important aspect for the vegetation index that we're going to perform. So it ensures consistency, accuracy, and it also helps to make sure that we can use the special chlorophyll index. So let's take a very quick peek. So here we have our Landsat scene that we got for free. This is the rapid eye scene that we purchased. We're going to zoom in to our AOI. And we're just going to toggle it on and off. So you can see there's not a dramatic shift, but there's about a 60-meter shift between the two. So using Ortho Engine or Modeler or any of Geomatica's geometric correction methods, you can then quickly create an ortho image and co-register it to our Landsat image to perform much more provide much more meaningful information. And then orthorectification is a prerequisite to performing our atmospheric correction if we have rugged terrain such as hills and mountain where we need to provide a DEM. So that's one of the first important components. Then the next one is the atmospheric correction itself. So once again, I'm just going to show you the spectra plot. We're just going to compare, look at a few areas. As you can see that we have a much more common signature. So if I go to a barren soil area, we have a signature that's indicative of what we would expect for rapid eye and soil. Vegetation, we have a much more, I'll just adjust the plot, relationship is much more closer to what we would expect here. Now this little curve here is due to the red edge. And if we compare this with our at-sensor radiance value, you can see that we're really getting a lot of junk. I mean, these signatures are completely useless and really cannot make much value of these signatures. So this is the importance of performing an atmospheric correction, is now our information actually has meaning. And I just, on that note, want to spend a quick moment to discuss the value of PCI's atmospheric correction package. So this is a really wonderful wizard that we put a lot of development effort into. And one of the reasons that it's so wonderful is it significantly simplifies the process of performing an atmospheric correction of your imagery. Now, for those of you who are already familiar with the ATCOR or atmospheric correction workflow, either in our past packages or in other software, you are probably aware that it is one of the most time-consuming and difficult pre-processing tasks that you might be required to perform. There's often a lot of parameters that must be supplied. It can be relatively confusing, so it does definitely require a more advanced user. And it can be also very time-consuming to make the calculations. So what we've done is we've made atmospheric correction, we brought it back so that you no longer need to be an advanced user. You no longer need to be an academic in order to perform an atmospheric correction. We have a wizard that guides you step by step. So really now this becomes a more commercially viable operation, such as orthorectification. Orthorectification back in the early 90s and 80s was a very difficult task. So often people would settle with less accurate methods. But now with the tools and the development of the technology, it's become a very useful and meaningful and easy to do task. Well, atmospheric correction, that's the path that we're trying to take it on. It's a very useful task, very useful operation, and we're now providing the tools to make it a simple operation. So the first thing we do is we can load, for example, our ortho image, our rapid eye image in here, and then when we ingest the data, we automatically read all of the different metadata associated with it. And then we perform the necessary conversions or calculations to obtain our values. So it automatically identifies that it's a rapid eye sensor, provides the acquisition date, calculates the solar zenith and azimuth angles, calculates the calibration coefficients for rapid eye. This isn't so difficult, but for other sensors this is a very time-consuming task, and we support many other sensors for this as well. Automatically associates the channel to the correct band. You simply just point to an output directory and all of your products are provided. We have some advanced cloud masking, new cloud masking capability with a seeding concept, water masking, and improved haze removal algorithm. And as you can see, the wizard is guiding me through, and I'm really not doing too much. I can then point to a DEM if I want, and then we do all the necessary resampling, clipping, reprojection in the most accurate fashion depending on the ratio of the resolution of the DEM to your imagery. So you're no longer required to do any of these tasks, which is really wonderful. And if you are working in a flat area, we provide the average height for that area automatically, so you're pretty much ready to move on. We automatically estimate, so we can't get this perfect every time, but we estimate the condition of your area based on the date of acquisition and the latitude of the scene. The aerosol type you're still required, but then the viewing geometry, same thing. We automatically populate and calculate the correct sensor tilt and the satellite azimuth angles. And then the rest is once again fairly basic aspects or parameters of atmospheric correction. So these are just one, and then we're furthering to advance this even more. So the idea is that if you're not currently performing atmospheric correction because of the difficulty of the task, well, you should look into this package. It's a really wonderful tool that can allow you to even get more value out of your data, such as what I'm going to show you here. So that's my little spiel on our atmospheric correction package. So I'll get back now to our actual workflow. So once we performed our atmospheric correction, we can now compute different index for a different type of, different type of output that we're looking for. So the two that I've chosen are basically the mcarry method. So it's an index that's specifically tuned for measuring chlorophyll levels independently of the amount of leaf area index. Now, as you can see here, what this is saying is that even as it's medium dense to very dense vegetation cover, the index is very independent of these values. So it's much more affected by the chlorophyll measurements in the actual vegetation itself, as opposed to the density of the coverage. Now, of course, as we get to the lower end, so where there's very sparse vegetation, naturally our relationship, or naturally our index values are going to go down as a result that there's obviously no chlorophyll to measure if there's no vegetation. Now, the other one that we're going to compare our chlorophyll measurement, or our chlorophyll index value results, to what's called the MTVI1. And this was identified specifically in a hyperspectral paper, but it's actually, I applied it here, and there's still more testing to see how rigorous these techniques can be used in broad-based spaceborne sensors. But it's a really neat technique that you can attempt and use to see for the leaf area index. And as you can see, that as a leaf area index increases, our spectral indices also increase, and the range is much smaller. So meaning that regardless of the chlorophyll content in the crops, the index is going to be highly correlated to our leaf area or our density. And this is the paper in which these tables were provided by. So mcarry was also identified by Klaus Schelling of Rapid Eye as a suitable chlorophyll index which makes use of the red edge band. So this is actually one of his papers that were provided on it. And obviously he does mention that there still is more testing required to validate the robustness of these measures. But it's just a wonderful tool to attempt. So let's go quickly take a look at our results. and our three different fields that we were interested in. So I'm going to go to our first field here. So what we're looking at is basically, so I'll toggle this on and off so you can see the field. So what we have here is our M-carry results. And this is basically just showing a relative measurements of the chlorophyll content as described by the M-carry index. So we can see that it's relatively high and medium high in most of the areas. We have some issues perhaps here, and our largest issue tends to be right here. So the next thing we need to do is wonder, now is this a result of chlorophyll content, so stress or lack of nitrogen potentially in the field, or is it potentially that's just a very low leaf area index? So we cross-reference this with our NTVI1 of this field, and we can see that we get a similar relationship in this area here, as well as right here. So it is showing that there's a relationship between the two, which gives us the conclusion that the problem area is likely due to sparse vegetation cover and not nitrogen deprivation or just low chlorophyll measures. So as you see these results side by side, we can see that there's definitely a strong relationship between these. So I would be less inclined to take samples for lab analysis to look at the nitrogen content, and more I would probably go down there and look at the potential leaf coverage of the area. So let's move on to our second field. So here we basically have our field number 2, and what we're going to do is we're going to once again perform the same analysis. So we're going to look at it, and using the M-carry index, we can see that we have a major area of potential stress in the center of this field. This is a fairly large area, and we also have some areas of concern perhaps around here. Now if we cross-reference this with our MTVI index to look at the leaf area for this field, well, we can see once again that there's a similar relationship. If we take away and we actually look at, we can see that there's definitely some barren areas going on over here. And one other good way to take a look at that is to load the near-infrared band, apply the necessary enhancements. And you can see that we have a much lower as compared to our other areas. So let's see the conclusion that we're going to come to from this. So as you can see here, that when we put these two measures side by side, that we can see that there is a strong correlation once again between these two. So it's likely due to sparse vegetation as opposed to nitrogen deprivation. Oops. So finally, we're going to move on to our third and final crop that we decided to take and perform a further analysis on. So the M-carry shows a variety of signs of stressors or potential sparse vegetation. And let's just see how this compares with our MTVI1 computation. Well, and this one's interesting because we can see that there is some low values in certain areas, but there's also a lot of areas that don't match, particularly in this part of the field and down here. So if we look at and it's kind of neat that it doesn't match what the obvious pattern might be here. So let's take a look at these results once again side by side. So as you can see here, there is a clear pattern mismatch between these two. And so this might be an area that I might be more interested in sending, some of these areas over here, I might be more interested in sending lab reports or performing a field analysis on these regions to identify what is happening and why is there potential stressors in this area. So that concludes really the first component or the first use case of this webinar. So the second one is really a very simple and short one, which we're just going to show you a very simple method to perform seasonal monitoring with Landsat-8 and Geomatica. So we're going to perform NDVI change detection and demonstrate how it's a very fast and effective way to monitor phenology of your plants. So as we can see here in this example, in this screenshot, as we're measuring relative changes, we can see that the vegetation changed from June 4th to June 19th. So we can see where we had a high growth in areas which are notified as or denoted in the red color and orange. And then yellow and green is really areas of, particularly green, is areas of little to no change. And then the cyan and blue colors denote where there was a negative change, so where there was vegetation and then it became fallow. And then if we look at June 19th to July 5th, we have the same graph, but as you can see, it's a notably different result. So we're going to take a look at these results and just these concepts and why it's so useful. So let's open up our project here. And the first thing you have to do is you have to load your Landsat-8 imagery. So I have Landsat-8 imagery from 2013, 0604, and then 2013, July 19th, so this is July 4th and July 19th. And then I'm just going to very quickly show you how to load Landsat-8 imagery into Geomatica for direct use. So I'm just going to drag the mtl.txt file and then place it here, and then automatically I can select which of the bands or band combinations I want to load. So I'm going to choose the multispectral. And this image is from July 5th. So what's interesting, so let's take a look at the NDVIs. And once again, the NDVI can be simply calculated using the raster calculator. It's a very simple calculation. And then I'll show you how to basically use the NDVIs in a change detection with one of our change detection algorithms, which is very fast and very easy to get a quick idea as to the phenology of the different plants that you might, or the different fields you might be interested in. So I'm going to first take a look at the June 4th NDVI. So we can see that there is a lot of areas that are neutral, so not very high. Remember, this is not the change detection, it's just a pseudo color. So the blue is identifying very barren areas. Green is identifying areas that have some moderate or average NDVI values. And then the orange, yellow, orange, and red are identifying areas where there's a higher NDVI value. So if I look at this, and I compare it with the next one, we can see that there's a dramatic change. So only 15 days later, we get a significantly higher NDVI values for a lot of the same areas. And this is really a result of the fact that we had many fallow fields earlier, and this is now the beginning of the emerging areas during the growing season. So emerging crops. And then finally, if we look at the NDVI for another about 15 or 16 days later, we can see that it even gets more thicker. So this is still as it's starting to grow and transition from the emerging period into the peaking. So we're just getting continuous growth. So we can monitor that very quickly visually at looking at the NDVI values, but we can also perform a change detection and get a more meaningful result. So let's look at the change first from June 4th to June 19th. So this is our change map now. So it's using a similar color scheme, and I'll describe it in a second. But actually, before I do that, I would like to just quickly show you the algorithm I used to calculate this. So you can go to Tools, Algorithm Librarian. You can choose what's called Optical Change Detection, or CHDET-OP, and you can find it here if you type in Optical Change Detection. And then really, for the first branch, so it wants your newest image, so we can identify our Landsat imagery, or sorry, our NDVI image. So we'll take the newest one first. So I'm just going to look for our NDVI. And then in the reference, we want the older image. So we can go to inputs here, and we can choose, for example, in this case what we did is just a simple channel difference, and then we have positive, and then what this is going to do is it's going to give us a map where it's going to actually color code the changes based on where there was a decrease in vegetation as opposed to an increase. So it's a very nice algorithm. It's actually it's relatively fast to run, not quite fast enough for the amount of time that I have left here. So I must conclude very soon. But it's just a very useful algorithm. And then there's other options in terms of just, as opposed to just the difference. So there's other ones such as magnitude, ratio, and some of them also will produce a percentile change. So you can look at the relative change based on percentiles, which is also a very interesting way to view change. So I'm just going to zoom in here very quickly and show you that the cyan colors are identifying fields between the two dates where there was a decrease in vegetation. So if we focus on this field here, you can see that there was vegetation in our earlier image, and the image afterwards, the vegetation was removed. So that's what's being identified by this change. And then obviously the red and purplish colors are identifying where we have the opposite effect, where there was no vegetation or very low NDVI values, and then it changed to an increase, and then it increased significantly between the two dates. So you can see here's the initial one, and you can see that it increased fairly dramatically. And of course we can do that for the other image as well. So if we look at our other change, even though the NDVI was really high in this, the relative change between the two dates was not so high. So if we look at this, we can see that there is some change, for example, in these areas again. But as an NDVI, or sorry, if we look at the NDVIs, you can see that it's not too significant. So this is really just a very simple method to perform a very quick change detection. And another nice component is that the Landsat imagery comes, for the most part, very well aligned. So very limited. For this type of analysis, you don't have to do a lot of post-processing. You can pretty much get the results almost immediately using Geomatica. So this really concludes our webinar, or the technical presentation component of our webinar, and I'd be happy to pass it over to Jason again. So thank you very much for your time.
Excellent. Thanks, Sean. That was fantastic. I hope everybody enjoyed what they saw so far today. Before we get to the Q&A, I do have one last poll for everybody here, and that concerns what you have just seen. So, having seen what Sean was able to show you, do you see any barriers to implementing this yourself, or any drawbacks that you might see? Perhaps you need much higher resolution imagery than what we've used in this demonstration, and that's a barrier to implementation. You might need to do this much more frequently than you can with remote sensing imagery. Perhaps the qualified analysts to look at this data, you're concerned about that, or maybe you just don't want to do it yourself and are looking for a service, somebody to give you the answers based on what we've already seen here. And as always, there could be other barriers to you adopting this.
Perfect.
Thank you, everybody, for taking part in the polls. Pretty even split across the board on this one as well. I want to thank everybody for taking part in all the polls. It really does help us deliver better webinars and deliver better products. We are getting pretty tight up to the hour, so I'm going to run through the last of this quickly so we can get to some of the questions. Now that we're done, I urge you to try what you've just seen now, if you're so inclined. Today's demo used the following packages: Geomatica Core with a satellite ortho package, the production toolkit, Auto GCP, the at-core atmospheric correction module, and portions of the demonstration were done using Modeler, which is PCI's automation toolkit. Now, Modeler there on my slide is there in gray. It is the only thing that we used today that is actually part of Geomatica Prime, which is sort of the next step up from Geomatica Core. If you're interested in learning more about Modeler or Prime, you can contact a sales rep or an authorized reseller in your area, and that's available on PCIgeomatics.com. However, with the exception of Modeler, everything you saw today can be done with a trial version of Geomatica, which you can find with a big download now button at PCIgeomatics.com/Geomatica. And the website there is also there for how to obtain the Landsat imagery. This is not the only place that Landsat imagery is available. It is our preferred method of downloading Landsat imagery, but there are other methods of downloading it. And the tutorials on how to download the imagery, as well as other tutorials and demonstrations, can be found on our YouTube channel at PCIgeomatics.tv. So feel free to visit any of these links at your own time and learn a little bit more about what we do. We will be delivering slides and a recording of this presentation to everybody who attended today, so don't feel like you had to write anything down. And if you did write anything down, I apologize, because we're going to be sending out the recording to you shortly anyway. So now we're going to go to a few questions from the field up against the top of the hour. But Sean, if we have a question concerning optical change detection, and somebody is wondering if the two images have to be resampled to the same scale or resolution if you're using different sensors looking for the change.
Yeah, if you're doing change detection, obviously it's important to make sure that you have the two data sets resampled and that you actually upsample the one data set to the other one. Now, I'll have to check with, and perhaps Peter, who I think is on the line, might be able to answer about whether or not our change detection algorithm automatically upsamples the lower resolution or the higher resolution to the lower resolution sensor, but I would have to check on that one. So it is definitely a necessary operation. My only question is, does our optical change detection do it automatically?
Excellent. I think that's a clear enough answer. And if it isn't, I would also like to remind everybody on the line that if you have a question that might be a little too technical for the time constraints we have right now, we will be handing out a text-based version of the questions and answers that we've had from this that we will be able to give a more nuanced answer to. We have a question about the results of the atmospheric correction, and is how do you check or validate these things to know that they're accurate? Is this more of a looks good to the eye thing, or is there a quantitative way of measuring this?
No, there's definitely a quantitative way of measuring it. Now, actually, Dr. Richter, the developer from DLR who created the at-core workflow and algorithm, basically had performed a lot of measurements and studies to look at the spectral response and also go into the field of, in terms of looking at the reflectance values of different crops and different sediments on the ground in order to identify what their signature should look like in a atmospherically corrected data specifically for that sensor. So the quick answer is what you do is you would compare the signature that you're getting for a field that you know the species type, or for example, the ground cover type, so a specific type of soil. And then you would cross-reference that with the library of signatures that we actually have in our atmospheric correction package. And if the measurements are highly correlated, or not correlated, but very close to what you would expect for that as compared to the library, and you do this with a few different checks in your image, then you can come to the conclusion that for the most part it's fairly accurate, that you have a higher level of accuracy. So yes, there is it's important to check your results of your atmospherically corrected results or image, and definitely doing it by eye is not recommended.
Excellent. Thank you, Sean. And with that, we have hit the top of the hour. So I thank everybody for joining us today, and thank you for your questions. Thank you for taking the time. Thanks to you, Sean, for putting together and delivering an excellent demonstration. And like I've said to everybody, we will be delivering the slides and the recording and answers to questions we weren't able to get to shortly. And we hope to see you again or hear from you again soon at a webinar in the future. Thank you very much. Have a nice day.
Thank you.